Okay, good. So I'm going to quickly review these t-tests and confidence interval estimate for mean. Right? So the one sample inference for mean, right? One parameter of a population. And if you recall, when we were studying this, we have a couple of theorems actually help us to reach the sampling distribution of a mean. Right? One theorem is that if you're taking a random sample from normal population, the sampling distribution will be also normally distributed. Okay, so that's one theorem. So it's just in case you collect data from normal distributed population, right? Then you have this t-test or confidence interval estimate that you can use. And the other theorem is a central limit theorem. Central limit theorem says that if you take a random sample from non-normal population, well, it is fine. If your sample size is large enough, sample mean will be normal, approximately normal. So again, you can use the confidence interval estimate that we have learned for estimating mean of a distribution. And in fact, we can also do hypothesis testing, right? And if you recall in the class that we emphasize on the t-score, right? So when we do confidence interval estimate, we use a t-score right, in the formula. And also when we do hypothesis testing, we do a t-test, right? Although in most of the book they mention z-test, but z-test is not really used often, right, in practice. When you use a software, everybody uses a t-score, t-distribution to do the confidence interval, right, to calculate margin of error, and also use a t-distribution to do the test, okay? So this just tells you that in order to use a t-test, right, or a confidence interval estimate for mean with t-score, you got to have either one of these conditions satisfied, right? You're sampling from normally distributed population, or if your data is not from normal, you got to have large sample, okay? So you have really, when you're doing a study, if the sample is small, you definitely need to check normality to be sure that you can use a confidence interval estimate formula with a t-score, right? Because that's actually the distribution of assumption, right? But when sample size get large, right, sample mean will be normal, okay, and estimation for standard deviation will be pretty good, right? So actually sample size large, it's safe to do that, right? You don't have to check for normality, okay? But sample size small, you definitely want to check for normality, okay? And also this is just helping you to understand the relationship between the parameter of the sampling distribution of mean and also the parameter of the distribution you're sampling from. This tells you that the sampling distribution, the probability model for sample mean, will have a mean that's the same as the mean of population, right? And standard deviation of sample mean is a standard deviation population divided by square root n. And you did some practice, I know, with a sign problem also, right, for using this theorem, okay? And the graph over here, that I'm just trying to show you that, right, when we have a sampling distribution of mean that being normal, and if you look at the standard score for the distribution of a sample mean, right? It is standard normally distributed. If the standard error of the sampling distribution is known, is given, I should say population standard deviation is given, all right? So you use that to get the standard deviation for the sampling distribution of mean, all right? And in that case, right, if you look at the standard score distribution, right, or the standardized distribution, it is the standard normal, okay? But if you estimate the standard deviation using the sample standard deviation and use that to standardize the sample mean, especially when sample size is small, the standardized score, right, or z-score, or I should say standard score, right, for the distribution of the sample mean actually no longer follow standard normal distribution, it follow a t-distribution, okay? And so that's why earlier we learned a confidence interval estimate for mean. We didn't use z-score. We actually used a t-score because we estimated the standard deviation by sample standard deviation. All right. So the actual distribution, if you try to standardize sample mean using the estimated standard error, those z-score, right, follow a t-distribution. All right. So anyway, in practice, every time, most of the time, when you try to estimate the mean of a distribution, this is the formula you use. So you use a t-score, right? And remember, the assumption behind this is normality, okay, or large sample, Okay, if you have large sample, that's great, right? You don't really have to have normality. But if you have small sample, especially, right, you got to check for normality. I think you did that, right, in your assignment. Okay, so that's what we have studied, right, in the past few weeks. Okay, and so this is again that formula. Right? This is just telling you that this t distribution actually converges to z squared. So if sample size is very large, this formula, the result for this formula, it will be very similar to a formula that you learned first, all right, that has a z-score there. Right? But like I said, when you're answering any question in the class, doing homework assignment, all right, don't worry about the confidence interval estimate for mean with a z-score there. Right? Everybody use t, so keep that in mind. Right? When you run the R commander give you a confidence interval using a t-score, right, for estimating mean. And then you deal with sample size issue, right, for estimating mean of a distribution. This is a formula you use for estimating sample size that is required in order to achieve certain goal in terms of margin of error, right? This B, again, should be E, right? Sometimes I use B, sometimes I use E for margin of error, right? B stands for boundary, right, but anyway. So you can replace this by E. Okay, so that's a formula. I think you use that in the assignment. And also, you have studied, and you actually in the assignment, you also use this formula to actually calculate the confidence interval for estimating the population proportion. Right? So, two versions of it. Right? One's using interval notation, one's using the point estimate plus or minus margin of error. Right? So I guess you should be able to do this now by hand, and with the software R Commander, remember, if you use R Commander to do this, actually it gives you an unbiased estimate for a confidence interval, and it uses a different formula, not this one. All right, so I ask you to actually download a HMISC, right, package, and in that package there's a binomial confidence interval option for you to actually compute confidence interval that is using exactly this formula. Right, so you did that in your assignment, so that's great. And for interval estimation, all right, for a margin of error, you can actually figure out the sample size to achieve that goal. Depends on whether you have some prior knowledge or pilot study, right, some information about proportion, or you have not. Right, there are two versions of formula that you can calculate the sample size. Right, so that's good. And then after that, you studied hypothesis testing, right? So you know that the class, I recommend the 4 steps, sort of like a 4-step method, right, that you can actually go do the confidence interval estimation. The testing hypothesis, right? Starting with hypothesis testing, stating hypothesis, and then finding the calculating test statistic, and then you want to have a decision rule, and the decision rule always the same. Right, that you have a p-value less than alpha level, you reject the null hypothesis. Right. Now you're going to learn so many tests. There's still more tests to learn. Right, and that decision rule always the same. If you do p-value approach, once you have a test statistic, you will calculate the p-value and use that p-value to make decision. If that p-value less than alpha level is significant, then you reject the null hypothesis. Rejecting null hypothesis means you support the alternative. Right, so anytime you try to conclude your test, you want to not only say you reject or not reject null hypothesis, you want to comment on alternative hypothesis. Right. So when I grade your homework, I will also look for that. If you don't have that, maybe some point deduct. I just like you to have that habit. Right. Don't just say I reject null hypothesis, because in the future, if you write a report, right, if you just say I reject null hypothesis, the reader won't understand what you mean. Right. So you have to explain that. Right. And of course, then we learn one sample t-test, and this is a test statistic formula, and you use the R command to do that, I guess most of you, right? So probably when you do it too many times, you probably forget what really gets you that, all right? It's important to know what's going on, especially just the first test you learn, t-test. If you understand everything in t-test, it'll help you a lot in understanding the test procedure in the future, right? You may learn the test for maybe standard deviation of proportion or parameter, other parameters, right? The concept, basic concept is the same, okay? And the the assumption behind t-test is like that assumption behind the confidence interval estimate for mean, right, with a t-score. You have to have a normal distributed population. If you don't know the variance, you have to estimate it. Right? Or if you have a large sample size, then estimation for variance or standard deviation usually is pretty good, right? And you can still have a normal distributed sample mean and be able to use the t-test to do the problem. And then there is also sample size issue, right? So before you do your study, you like to know how big a sample size you will need in order for your test to achieve certain power and to detect certain effect, right? Certain size of effect. So this is one version, and then there's another version. If you specify your effect size in terms of number of standard deviation, and whatever that number of standard deviation, you put it in a denominator, so you don't need to have a sigma in the formula, right? So for using such a formula, you don't really need sigma, because some study, you never have a chance to really do a pilot study, right? Maybe the cost of the experiment is pretty high, so you can just want to launch that one study. You wish to determine the sample size, and sometimes people use the number of its effect size specified in terms of number of standard deviations, right? So you can use this formula to do that, okay? And this is just a two-sample situation if you want to figure out the sample size, right? And then we study the sample proportion. We say that the behavior of sample proportion is like a sample mean, right? If your culture data is 1 or 0, right, sample proportion is like sample mean. So when sample size is large, central limit theorem applied to sample mean, I'm telling you that statistic will be approximately normal. So we actually, because of that, we realize the sample proportion, the distribution model, right, for sample proportion is also normal, right? And so the confidence interval estimation formula is almost there because it's the same concept. So if you know the standard error for the distribution of the sample proportion, then the confidence interval estimate will be like this. This formula looks very similar to confidence interval estimate for mean, right? Except for we only did with large sample, right? So you don't have to worry about normality, right? Sample size get large, central limit theorem tell us that sample proportion is normal. And we use a z-score. We don't use a t-score there, right? So that's interval estimate for proportion, okay? And there's large sample size condition. What's considered large sample size? So a lot of books says that if you expect each of the category on your sample, right, that has more than 5 counts, and large sample sets condition satisfied, right? And some books say 10, right? But it's just based on the experience. Usually when you're doing this kind of study, your sample size is much bigger than this, right? So you don't have to worry about this, right? And then there's also hypothesis testing for proportion, okay? It will be a z-test. And this z-test will be very similar to the z-test that we went over before we learned the t-test for mean, okay? So the test statistic for testing proportion will be just standardized sample mean, right? And using the proportion under null hypothesis standardize it, right? To see how extreme your evidence is compared with the proportion under null hypothesis. So it's a z-test. If you know it's a z-test, and the rest of the thing will be very simple, right? Once you have the z-test, you have that z-score, you look up a standard normal distribution, you'll be able to find out its right tail area or its left tail area to decide your right tail test p-value or left side test p-value, okay? Or multiply the smaller tail area by 2, you get a two-side test p-value, right? So testing for proportion, right, it's just very similar to testing the mean, almost similar to t-test, except for now you use a standard normal, use a z-score, right? So this is what you study this week, okay? So let me quickly go over one example with you, okay? This is a situation that we try to see whether in a certain large community, the percent of people who have no insurance coverage during the past 12 months is not 10%, right? Maybe in the past was 10%. We believe that right now it's no longer 10%, right? So you don't know whether it's higher or lower, but you don't care. You just want to test whether it's different. So what you do in this study, actually, he collected a sample of 1,000, and 122 of them answered that they did not have health insurance, right? So with this data, you should be able to calculate the confidence interval estimate for proportion right there, right? So that's not a problem. However, this problem here is testing hypothesis. You want to see whether the percent of people who have no insurance coverage is statistically significantly different from 10% at 5% level of significance. Right? So how do we do this? Step by step. First step is stating hypothesis. Right? We want to test whether the proportion is 10% or not. Right? So null hypothesis 10%, alternative hypothesis not 10%. Okay. And so next step will be computing that z-test statistic. Okay. Help us understand whether that evidence is statistically significantly different from 10% or not. So we standardize that evidence. Right? We have 122 out of 1,000, so the sample proportion is 0.122. So we standardize that using the proportion under null hypothesis. We subtract that, divide by standard error for sampling distributed sample proportion under the null hypothesis. So this is the formula we use. Everywhere you have a p0, plug in the proportion under null hypothesis, and sample size is 1,000. Right? So we get a number, z-score 2.32. And this is a two-sided test. Right? So if we can find the area to the tail of 2.32, which is a 0.01, right? Or if you look up the table for more accurate number, I think it's probably 0.0102, somewhere like that, right? I run it to two numbers just to simplify the thing, okay? So area to the right of 2.32 is 0.01, and we're doing two-sided tests, right? Based on alternative hypothesis, we know it's two-sided test, so we double that, so it's 0.02, okay? And remember, we want to test this hypothesis 5% level of significance. Now, p-value is 0.02, so it's actually less than 0.05, right? So our rule is, the decision rule is to reject null hypothesis, p-value is less than 0.05. Now we can draw a conclusion. P-value really less than 0.05, right? So we're going to reject the null hypothesis. You're going to conclude that there's sufficient evidence to support the alternative hypothesis that the percentage, right, of people who have no insurance coverage is statistically significantly different from 10%. Okay, so this is the way I like you to state, right, your conclusion. Right, really explain what's going on. Do not just put I reject the null hypothesis, right? Okay. And also the language you use. When it comes to hypothesis, null hypothesis, we always say reject or do not reject. Right? And alternative hypothesis, we always say support or do not support. Right? Try to use that language in the class. Right? Now, outside the class, when you start doing the research your own, and you probably can change these statements into something that more closer to your practice. Right? But at this point, please try to follow this pattern, right, to write your conclusion. So that's what we do for testing proportion of a distribution. Okay, that's pretty simple. If you know your t-test, this z-test is pretty simple. Okay. Now, a lot of time people don't care about doing one-sided tests. They just do two-sided tests, right? So if evidence is actually supporting your alternative hypothesis, and you end up getting two-sided test p-value that is smaller than 0.05, then one-sided test p-value is definitely less than 0.05, right? You see, one-sided test p-value is actually 0.01, twice as I give you two-sided test p-value. So if you do two-sided tests, and you realize your evidence is supporting the alternative hypothesis, then you can conclude, right, that actually the proportion is significantly greater than 10% based on what you observe, based on your evidence. Right. So those of you who have used SPSS in the past, you probably realize that when you run SPSS, it always gives you a two-sided test p-value. It never give you one-sided test p-value, right? Some students feel that it's so inconvenient. My professor asked me a one-sided test, I don't know how to answer, right? But if you have a good idea, then actually if your software only gives you two-sided test p-value, you should be able to convert it to one-sided test p-value, okay? Whenever your evidence supports your alternative hypothesis, then if you have two-sided test p-value, you just divide it by 2, you get one-sided test p-value for that test. Okay. If your evidence does not support the alternative hypothesis, in fact, support the other side, then the p-value for one-sided test should be half of the two-sided test p-value subtracted from 1. So you're going to have a large p-value since your evidence is not supporting your alternative hypothesis, right? So anytime you have a two-sided test p-value, you convert it to one-sided test p-value easily. Okay, so hope that makes sense to you, right? It's important to know that. Okay. Okay, so that's actually like 3 weeks ago. That's what you studied, and then last week you studied multiple population, and you try to do paired sample or two independent sample test, or ANOVA, that is a procedure that you can use to test a mean, comparing mean for multiple sample. Right? So that's what I'm going to review right now, right? Comparing two means, right? Paired sample test and two independent sample tests. I think you studied this. And paired sample tests, actually, you have data collected by pairs from each subject, right? So you have one sample of subjects, but for each subject you observe two observations. And usually when we do these tests, right, the measure that we are interested in is the difference, right, between that pair of subjects, a pair of observations from each subject, right? So the pair sample t-test is exactly the same as one sample t-test, right? You just have one extra step, right? Before you go to one sample t-test, you calculate pair differences first. And then you use the average of those pair differences, right, as a sample mean, right, and in doing the one sample t-test, right? So if you have a software that doesn't have a pair sample t-test, that's great. Actually, that's fine. Actually, that's great, right? Sometimes a lot of software give you the pair sample test, but the test is not flexible enough. Usually, they give you a pair sample t-test without an option for you to specify the test value, null hypothesis. So you can only test whether the average of the difference is different from 0 or not. Right? So make it not so flexible. But if you do know that it's really just a one sample test, you can actually just calculate the pair differences and use a one sample t-test on the data. Okay. So just this slide just help you, hopefully you understand. All right. We have a sample of pair differences. We'll find the mean of the pair differences, find the standard deviation of pair differences. We can do a one sample t-test for that. Right. And this delta 0 is really just the mean of difference on the null hypothesis. Okay, so that's a pair sample t-test. So your hypothesis, null hypothesis would be the average of the pair differences is equal to specific number versus one of these alternatives. Depends on what your research interest, what's your interest in your research. Right? So this is an example. I hope you have gone over this. Right? It's about evaluating the fact of a weight loss program, right, or diet program. And so there is a weight, there are 12 subjects involved in the study, and before the program, their weight are measured in terms of kilogram, right? And then after the program, you get the weight. So what we do, we use after. If you use after minus before, if there's really reduction, if this program is really doing something for reducing weight, you expect most of the measures should be negative. Right? In fact, in this situation, really most of them are negative. There are a few positive, right? That has no effect. Okay. So to do this, actually, what we really need to do is just do a one sample t-test on these differences to see whether the average reduction, right, is significantly different from 0 or not. Especially average difference here is actually should be less than 0, right? If you're using after minus before, if you use before minus after, then you expect most of them are positive, so you expect that would be really the reduction, right? If it's a reduction greater than 0 or not. Okay, so in this problem, really doing the one sample t-test on this data to test whether average the difference is less than 0 or not. Right? So we can do a paired sample t-test for that. We calculate the average of the difference, calculate the standard deviation, and then standardize our sample mean. All right, doing the regular t-test, you should be very good at it now, right? So we have a t-score of negative 2.573, and you can look up a t-table if you try to use a table to solve the problem, okay? But decision rule, again, it will be that p-value less than 0.05. If I want to test this at 5% level is significant, right? So, in fact, if you look up a t-table, you will find out that the t-score will have a tail area that's even less than 0.025, right? If you look at the t-table, there is a score of 2.205. Our score actually is 2.573, even further from 0, all right? If you have a t-score 2.201, the tail area is 0.025. Ours is 2.57, so the tail area should be even smaller than 0.025. So that's less than 0.05. You will reject null hypothesis. If you use Excel software, right, or use R Commander, right, it will give you the exact p-value there. It's about 0.01296, right? So that's a small number, less than 0.05, so you reject the null hypothesis. Right? While you're answering question for Web of Science, some of the questions they ask you to use a software to calculate exact p-value, right? So if that's the case, you should use a software, right? Now, if they didn't give you the raw data, you will use Excel, right? With the t-score that you compute, use Excel to help you to find the p-value. If they give you the data, I guess you would definitely, if I were you, I would just use the R commander to run the t-test to get the p-value, right? To get the exact p-value. So this is what I did with the R commander using their pair sample t-test option, because I know that what they want to do is just test whether there's a significant difference, right? So most of the pair sample tests is for you to test whether there's a significant difference. They're not good for testing whether average of the difference is equal to a certain number, greater than 10, greater than 5 or not, right? So just for testing whether there's different pair sample t-tests is good, right? So I just ran it and I get a p-value like this, okay? And I did a one-sided test. True difference is less than, actually I did a one-sided test, right? The p-value is this. Okay, two-sided test p-value will be actually 0.2, about 0.25. Okay. How do I know whether I did a one-sided test? Here it said two different means is less than 0. That means I choose the one-sided, so it has less than. Otherwise, it would say not equal to. Okay. And plus, it gives you a one-sided confidence interval. Okay. Usually, if you pick a one-sided test, it will give you a one-sided confidence interval. But in our class, anytime I ask you to do a confidence interval, please do a two-sided confidence interval. Right? That's pretty much standard. Every time when people try to report a confidence interval estimate for mean, for proportion, they will do a two-sided confidence interval, unless there's a special reason for it. Okay. So that was a pair sample t-test, right? Now, while you're doing this, once you find that pair differences, let me go back to the. We have actually 12 pieces of data. We have this 12 pieces of pair differences, and we use that to do the test, do a t-test. Okay. This is a small sample, and you have to estimate the standard deviation. So there's an important condition you have to check, that is normality. Right? So you got to check for normality for this. And I think you know how to do that, right? In R commander, just check on summaries and Shapiro-Wilks normality test to test normality. So you got to do that. Right? In practice, you got to do that. So to make sure that you do the right thing, because if your data is not normal, if you try to do a t-test, right, the assumption is not true, right? So your test is going to be, you're going to decrease the power of a test, right? Your test will be not sensitive enough to detect the difference. And you know that you have studied this week a non-parametric test, right? If you do have a situation like this, you should try to find a non-parametric test. Non-parametric test may have a better power when you have a data that is not normally distributed, right? Especially if a data that's heavily skewed, right? You want to try non-parametric tests, okay? It'll have better power and sensitivity in detecting a difference, okay? Because the non-parametric tests usually just don't have a strict distribution assumption, right? Your distribution of population don't have to be normal, can be any shape, right? Okay, so that was a pair sample test, right? Pair sample test, again, your data comes in pair. That's very important, right? So we usually call this, sometimes people call this related sample test, because the two samples are actually related, right? The two observations, they're both from the same subject, okay? Sometimes you may have studied, like you're studying, you make a pair observation from twins, right? You know that the pair of data are from twins. Twins have some similarity there, right? So sometimes if you study twins, you can consider that's a pair sample test. Okay, so you have to read the data carefully to see how data is collected, right? A lot of students will use a two independent sample test on pair sample data, which is not a good idea. The reason that they do the pair sample test, right, is for reduce possible error. Okay. If I do this study, I try to evaluate the effectiveness of a program. So I use one group of people. Actually, I randomly select two independent group of subjects, right? One group asks them to do exercise or goes through the program. One group don't. And then I try to compare the average weight after a few weeks. It's not going to be fair, right? Because these are two groups of people, right? You may be one of the group that just they don't do exercise, their weight are really low, okay? And so it's just not fair. So for study like this, it would be better if you make repeated measure, right? So observe subject first, and then have the subject go through a program and observe the same subject again, and to see the reduction, instead of having two independent samples. Okay, so there are reasons for this. And when you're doing this approach, the standard error will be smaller. So if you go home, try to run this with a pair sample test, and also use the same data run the two independent sample t-tests, you'll find out that the standard error for pair sample test is smaller, right? So it has its advantage, but you have to apply to the right data, right? If you apply to the wrong data, you have two independent samples, but you apply the pair sample test to it, it will be terribly wrong, right? You actually just reduce the error without a good reason, right? For error that you cannot reduce, you actually use the wrong test to reduce it, all right? So your outcome will not be correct, right? So make sure you read you understand the problem correctly and apply the correct method for it, okay? So that was pair sample test. And there's a situation that you have two independent samples, like this example that you have gone over, right? That we have actually two independent samples of cigarettes. One sample of filtered cigarette and one sample of non-filtered cigarette. We want to compare it whether there's a significant difference between the average amount of tars in these two types of cigarettes, right? So this is a good candidate for two independent sample t-tests, right? Because these are actually two separate samples, right? Filtered and non-filtered cigarettes. So if you do this, actually the hypothesis, right? This is the kind of hypothesis that I prefer to state, right? That mu1 minus mu2 is equal to certain number. That means the difference between the two population mean is certain number, right? So maybe the first population mean is greater than second population mean by certain measure. If that's a null hypothesis, your alternative will be that difference is not that number, or that difference is greater than certain number, or that difference is less than certain number. I prefer stating the hypothesis in this way. If you use a math expression to do that, right? And like I said, while you're stating these hypotheses, you can actually write a sentence if you want. If you're not feeling comfortable with using math notation, right? Write an expression. Like here, you just say the difference between the two mean is equal to certain number, right? The average amount of tar from the first cigarette, right, is or difference between the amount of tar, right, between the mean amount of tar in these two cigarettes is equal to a certain number. Okay, and you can have the alternative as difference between mean is not equal to, or the first population mean, the filtered cigarette, right, the mean is greater than second, the non-filtered cigarette by certain amount, something like that, right? So you can write a sentence instead of having to write these expressions, right? Sometimes I think for people, it's easier to actually decide whether you have right-sided test or left-sided test if you use this greater and less, right? But you can read those, right? If you write it properly, you watch out those greater than and less than words, right, in your statement. You should be able to use that to help you to determine which side test it is. But anyway, for testing difference between two mean, of course, difference of two sample mean is the most important measure, right? And the structure of the test will be similar to one sample test. Remember one sample test? We study one population mean, so we try to understand the behavior of one sample mean, right? This time we try to study behavior difference of two sample mean. So we use difference of two population mean. So we use the difference of two sample mean as the statistic to study this, all right? And so we need to know the distribution pattern for this, just like when we're doing one sample situation, right? For two sample situation, difference of two sample mean actually also follow a normal distribution. Mathematicians have derived that, right? And in fact, the condition very similar to one sample test. If the population is normally distributed, the difference of two sample mean will be also normally distributed, okay? Or if you have really large random sample, the population is probably not normal, but it's fine. Difference of two sample mean will also be normally distributed. So that's why when you do a t-test, you have to check for normality too. But when you do t-test, you want to check for normality. You want to check the normality for each of the sample because you have two populations you're studying. You want to know whether each of those populations are both normally distributed or not. Right? That's the assumption. Okay, so when you check normality assumption, you have to use each sample, right? You have two normality tests over here. Okay. But anyway, while you're studying this, you realize probably that there are two situations, right? One situation is that when two population variants, right, are not the same, there is a version of formula, right? This is the t-test statistic that you use for testing the hypothesis. Okay. When you do it this way, right, since the variants are not the same, so you use the sample variance to estimate each of those population variants in the formula. But the degrees of freedom, it's a very complicated formula there, right? Usually you have a fraction. And the other situation is if you assume variants are the same. If you assume that variants are the same, then each of those variants will be estimated by the same formula. We call this pooled estimate for the common variance, since we have common variance there, right? There is a formula for estimating that pooled estimate of common variance. That's this. You're pooling the sample variance for both samples together to come up with one estimate. And some people think that this would be a better way to estimate the variance or standard deviation, right? So you're using larger samples since you can assume variants are the same. So you're using larger sample for estimating that common variance. And if you do it this way, you have a t-test. That t-test with degrees of freedom n1, total sample size -2. Okay, so I hope you realize that. And while you're reading, if you're reading the textbook from the website, right? If you click read it in website, you probably see that they actually emphasize more on using. They prefer using this approach. They prefer using unequal variance approach, right? So if you do have equal variance just a special case of this, right? So you won't make much mistake, right? The only problem is probably when you try to estimate the variance, so you have smaller sample for estimating those variance. That's the drawback, right? And why there's another reason for doing this is using this is that we have this assumption of equal variance. So in order to pick either this one or this one, you have to check whether variants are the same or not. And while you're doing that, you're actually doing a test. There is so-called an F-test for testing the equality of variance. And when you're doing an F-test for making decision, remember, anytime you're doing hypothesis testing, you want to specify an alpha level, right, to make decision, right? So let's say you do an equality of variance test, you get a p-value of 0.07, okay? So it passed the 0.05, so you say, okay, well, two variants are about the same. But while you're doing that, you remember that alpha is probably a committing type 1 error, right? So you go through that test, right? While you're doing this whole t-test, you do a test of equality of variance, then do a t-test. So you're going through that process twice. People feel that, well, then you accumulate the probability, you're increasing the probability of committing type 1 error, and people don't like that. So some people say, don't bother to test the equality of variance. Just assume it's not equal, and then go through that, right? Go through the test. And that's what the Web of Science book emphasizes. They prefer that, right? But there are some statisticians and people don't like that. They rather you do it more accurate, right? If there's equal variance, you have a better estimate for variance, right? You should do that. So there are different opinions there, right? But while you're doing your homework, since you're doing Web of Science homework, right, you take this approach. Web of Science suggests that, okay? Just in case in the future you work on this a project with a boss, and you want to, if your boss asks you to check the equality of variance, you should know the reason why, right? There's a reason that you want to check equality of variance because you're going to have different t-tests. If the variants are not equal or variants are equal, you have different t-tests, right? So hope that makes sense to you. And this is exact the formula. Now, I think some of the Web of Science problem ask you to they give you mean and standard deviation. They didn't give you the raw data, which means they want you to practice this formula, right? So I think I put one question like that, right? So if you do see the data provided you just in terms of mean and standard deviation, there's no raw data, no detail, then you should just go to the formula and calculate t-test statistic. All right, it's a good practice. Okay, so that's two independent sample t-tests. So let's apply to this data. Okay, we have a sample of measurement for amount of tarts for 9 filtered cigarette, and also is that 9? Yeah, 9, and then 10 non-filtered cigarette. Right. So this is the measure. So we calculated their mean mean and standard deviation, right? So we got this data. The goal is to see whether there's a significant difference between average amount of tar in these two type of cigarette. So if we want to test whether there's difference, it's a two-sided test, right? So this would be our null. This would be our alternative hypothesis. The difference between mean is not 0, and difference between mean is 0. Okay. So if we assume equal variance, you're going to apply difference of the mean in the formula, and then you're going to use this SP squared, the pool estimate for the common variance, to figure out the actual variance that you can use in the formula, right? Those SP squared will be 0.12104, right? With that, you can compute your test statistic that is negative 1.745. And the degrees of freedom is total sample size minus 1. We have totally 9 and 10, 19 pieces of data. I'm sorry, minus 2, right? So 19 minus 2, you get 17. Okay. Then you can use that to solve the problem, to calculate the p-value and solve the problem. I ran the R commander, and I got the two sample t-test. P-value is about 0.099. That's based on this number, negative 1.74. Actually, I just round off, right? In my version, I get negative 1.745, right? I have the R commander to do it. It carry one more decimal place, right? So two-sided test, you get a p-value of 0.099, okay? Or if you use this score and then use Excel, you can figure out the same number there. If it's two-sided test, use the Excel t-invert and to find a t-distribution to find out the tail error multiplied by 2, since it's a two-sided test, okay? So you should get the exact same result. And so you can draw a conclusion. Now, if I test for equality of variance, in fact, I will show you how to do that. All right, later on, I would, when we go over some example, we can use the R commander, all right, to do this, and a t-test p-value is 0.0099, and test for equality of variance. This is actually outcome from SBS using Levine's test. It's 0.233. But anyway, if you have a software give you a test of equality of variance and give you a p-value that's greater than 0.05, that means you're not going to reject null hypothesis, right? If you test for equality of variance, null hypothesis will be equal variance, right? So you have a p-value so high, that means you don't reject equal variance assumption, so equal variance assumed. So that's why I picked that equal variance approach to do this problem, okay? And so your evidence is you do not support, there's not enough evidence to support the alternative because p-value is actually higher than 0.05. But if you notice this p-value at 0.09, this is two-sided test, right? If I'm doing a one-sided test, testing whether the average amount of tars in filtered cigarette is less than non-filtered cigarette. In fact, my evidence do support that, right? The average amount of tar in filtered cigarette is really less than non-filtered cigarette. So if that's the case, if I want to do a one-sided test, p-value will be half of this. And that will be actually 0.495, right? Just below 0.05. So you see, in this example, if you do two-sided tests, you do not reject null hypothesis. But you do one-sided tests, you do reject null hypothesis. So there's a situation like this. I think you probably have seen this.
Professor, I have a question.
Yes. Yes.
So if the question was, does it have less than 10, or is it just less? Then we would run the same test on our commander and just divide it by 2. What if you were to ask us if it was less than 1/10 of a point in this case? How do we run this test on R in this case?
I'm not exactly sure. Could you say that again? I'm not exactly sure what you're...
Okay.
Yeah.
So the question asked us if it was just the difference between the two
okay.
means,
correct? Okay, yeah, okay.
Let's say the question said, is sample 2 1/10 of a point less than sample 1, right? The filtered or non-filtered, right?
Mm-hmm.
So how would we run that test on R?
1/10.
1/10 of a point. Can you run it on R so we can see it?
You mean, so the difference is less than 1/10, or something like that. Yeah. R commander, yeah. If you have a specific... If you have a specific measure, right, for the difference, you just specify that. We're going to go do that, right? We're going to do that in a little bit. Okay.
Oh, okay, sorry.
Yeah, we're going to do that. I'm just trying to show you this, and then we will go to the R commander and show you some example. Right. Okay. That's a good question, right? If you do pair sample tests, there's not an option for that, right? But if you do two independent sample tests, there is an option for you to specify the difference. Okay. Okay. But anyway, so that one previous one was for equal variance assumed. Now, if not equal variance is not assumed or unequal variance is assumed, then you will have to use a sample variance for each of those sample, right, to estimate each of the population variance. So you get a formula like this, right? That's a t-statistic formula. But the degrees of freedom has to go through this complicated process to get the estimated degrees of freedom, okay? And this, unfortunately, this is what the WebAssign approach, right? WebAssign actually, they recommend that just don't worry about testing equality of variance. Just go through the not equal variance approach and estimate the degrees of freedom and use that to calculate the p-value, right? So if you have a Excel with you, right, once you get the t-score there and just put in this as the degrees of freedom, you will get a p-value from it. Okay, so that's, but most of the textbooks say that if you, since in regular class, a lot of time the instructor asks you to do a test, right? And then in the test, the instructor also give you the table, t-distribution tables. So if that's a situation, you don't have the software, then usually when people use a table to do the problem, they will run this degrees of freedom up, right, to 15. Because smaller degrees of freedom, the larger the spread of the t, so you have a more conservative result, right? So that's what usually people do. If you use table to do the problem, you always run up the degrees of freedom, right, to the nearest, to the lower integer, right? This is not like sample size. When we're dealing with sample size problem, we run up, right? But for degrees of freedom for t-tests, we run up. Okay. And so this is the outcome from the R commander Welch, two sample t-tests. This is actually, when you see this name, that means you're using unequal variance approach to do the t-test. And you have a p-value of 0.0938. That's pretty close to the t-test, two sample t-test when equal variance is assumed. So in practice, most of the time, the outcome is about the same. Okay. So anyway, this slide is telling you if you change your mind, and which is what I just mentioned, right? If you do a two-sided test p-value, you get a 0.009. That means what? If you try to do left-sided test, since our statistic is negative 1.75, the p-value for two-sided test actually is this small tail area to the left of this negative. This is your test statistic, right? This tail area multiplied by 2 to give you that two-sided test p-value. If I wish to do the left-sided test, I would just need the area to the left of it. So in this case, I would just need the 0.099 divided by 2 to get this left-sided test, if in case two-sided test p-value is given to you. And they also give you this test statistic value, right? And you're doing the left-sided test. If you are doing the right-sided test, you need the area to the right of statistic, okay? Now, the area to the right of this statistic actually is a large area. Actually, it's about 0.95, more than 0.95, right? That's a large p-value. Of course, your evidence not supporting alternative, right? So your p-value should be higher than 0.05. In this case, it's pretty large, right? Almost close to 1, right? So this is just trying to tell you that if people give you one-sided test p-value, you should be able to convert to two-sided. If people give you a two-sided test p-value, you should be able to convert to one-sided test p-value. If the statistic is given, right? You know whether evidence is in favor of alternative hypothesis or not. If your evidence in favor of alternative hypothesis, you're going to just divide the two-sided test p-value by 2 to get the one-sided test p-value, right? If you're doing one-sided test p-value, a one-sided test, but your evidence does not support your alternative, and if people give you a two-sided test p-value, you want to divide that by 2 and subtract it from 1. Right. Hopefully this graph kind of help you to understand that. And that same principle you can apply to non-parametric tests, which you are studying this week. Right. Sometimes some software only give you two-sided test p-value, for instance. You should be able to convert to one-sided. Right. Those of you who prefer use SPSS, again, like I said, SPS will always give you two-sided tests. If you want to do one-sided tests, you should use the same principle, right? But R commander, it's great. It gives you the option. If you do want to do one-sided test, there's a bullet for you to check for those different options, And also, you can do confidence interval estimate for difference between two population mean, right? So you have a statistic that's different two sample mean, and this is standard error for the difference of two sample mean. So this formula, if you compare this to the formula for estimating one population mean, it's very similar. It's a test statistic plus or minus t-score times standard error. But when you're dealing with difference of two sample mean, the standard error is this formula, right? So the idea is very similar. And if you have the software can do that automatically for you. But hopefully with the formula here, you can also do it yourself if you want. Right? So this is confidence interval estimate for difference between two means if that's what you're interested in doing. Okay. And here is just kind of review the condition that you can use the t-test for two independent sample tests. Okay. You got to know variance condition. Verified variance condition. If you don't want to take the textbook approach, you want to really, when you have equal variance, use one approach and not equal variance to the other approach. So that's one you want to check. The other is the normality assumption, right? Just like t-test earlier, you learned earlier, right? When you have sample from normal distributed population, you're okay. When you have sample that is relatively large, you're also okay. But if you have sample that is not from normal distributed population and the distribution is not normal with a small sample, right, then this test is not powerful enough, right? Then you probably want to choose number metric test, right? So the condition is similar to the one sample t-test, except for here we have two independent samples. So checking normality, you want to check each sample, right, to see each sample support a normal distribution or not. Okay. I hope that makes sense, all right? Let me, when you're dealing with, when you try to compare two population mean to see whether they're significantly different or not, right? Each of these are from a population. When you do the test, you actually, this could be the distribution of population 1, this, and there's a mean there. This is distribution of population 2. There's a mean there. So if there's really a significant difference between the two mean, right, the distribution pattern going to look like this. So you have two sets of data. If you do one sample, one test for normality using two sets of data, you know, you don't really have one normal distribution, right? You actually have data from here and data from here mixed together. You want to do normality test. You're testing that data. This is bimodal, okay? So that's not right, right? So while you're checking normality, you want to check normality for the first population. Use the first sample, right? Then check normality for the second population. Use the second sample. So you got to conduct two normality tests for it, okay? So hope that makes sense to you. Some of the textbook may ask you to test for residual, right? Residual really just a difference between data and their mean from the same data. So it's the same idea, okay? So I hope this makes sense, right? So when you're dealing with this problem, make sure you do normality tests for each sample, right? If you have more than two populations, then that's where the so-called one-way analysis of variance. So in the book, most books say analysis of variance, but there are so many different analysis of variance procedure, right? Analysis of variance is kind of like a title for everything that's related to this. In fact, almost everything in statistics is about analyzing variance, right? The variance is an important measure. You do t-test, there's a variance in there too, right? Do independent sample t-test, there are variance, analysis variance there too, okay? But this analysis of variance over here, right, which so-called also one-way analysis of variance because we're examining one factor, right? One specific factor, one specific variable, right? Categorical variable or grouping variable, right? And assuming that I have data from more than two populations, I want to compare whether there's a difference between the average of these different populations, right? Earlier, we looked at an example that is a difference between average amount of tar in two types of cigarettes, right? Now, you could have more than two types of cigarette. You have cigarette type 1, type 2, type 3, and you want to see whether there's a different amount, the average amount of tars on those three, right, population. Now, this one-way analysis of variance will be a good test for it, right? So one way means you have cigarette type as one categorical variable, right? In that cigarette type variable, you actually have more than 2 groups. If only 2 groups, the thing we just reviewed, 2 independent sample t-tests would be good enough. If we have more than 2, right, we have 3 or 4 or 5, then you can use the so-called analysis variance technique to do that. Okay. And usually a test like this is better when you're doing a so-called a completely randomized design, right? That you are able to apply treatment randomly to subjects. You have a group of homogeneous subjects and assign treatment to these subjects, different treatment to these subjects, right? And what I'm trying to say is from properly designed experiment, right? Not just from observational study, right? The test here really was originally designed for that. But then people actually use that also for just comparing mean of different population only, okay? So in our class, that's what we're focusing on, right? To see whether there's any difference between the average for different populations. So this is one example. It could be comparing the average heart performance for 3 different types of people, right? First group is non-smoker, second group is moderate smoker, and third group is heavy smoker, right? And then you have sample from each population, and you try to see whether there's any difference between the average heart performance in these 3 groups or not. And that's a good place for one-way analysis of variance, right? Or like I said, if we have 3 types of cigarettes, right? You want to see whether there's any difference in average amount of amount of tars in these 3 types of cigarettes, and that's this is approach to do it. Okay. Some of you may say, well, I just learned 2 independent sample t-tests. Why not I just test different between 1 and 2, and then test different between 2 and 3, and then test the difference between 1 and 3. I actually doing more thorough study. I can see all the difference between them, right? You can do that too, right? Actually, a lot of time you need to do that, right? But if I just wish to use one test, and that one single test can help me to see whether there's different amount of 3 or not, right? This is where this ANOVA, we call it one-way ANOVA F test, because this test, statistic actually have an F distribution, okay? So this one-way ANOVA F test actually has a reason there, right? If I do just what I said, or I do 3 tests to compare these 3 groups. So each test I have to specify type 1 error, right? An alpha or type 1 error for doing this test. So I'm doing the 3 times and actually accumulating type 1 error. Some people don't like that. They prefer to have one test to be able to just conclude whether there's a difference between them. And that's what this so-called one-way analysis of F test is about. Okay. So it's kind of like an extension of 2 independent sample tests to actually cover more samples, more population, I should say. And here are like 2 charts here. I think this case 1 is based on this data that I just have here, right? Plotting the heart performance index for sample 1, sample 2, sample 3. And so this chart actually give me some dot plots for the group 1, right? Those measure group 2, those measure, and group 3, those measure. If you look at this chart, you will see there's 3 clusters of data. They're so separate from each other, okay? So this helps us probably to understand that, well, there's actually a big difference among these 3 populations based on these 3 data. If you look at this data, these 5 data points, the variability within them is kind of small. They all cluster closely together. And the variability between groups is pretty large. So we can see that these are 3 distinct groups, okay? There is a possibility that you get 3 sets of data, and then the variability within group is very large, like this first sample, second sample, and third sample, right? And I have this, actually the vertical is the scale over there. If you take the average of these 5, actually it's the same as the average from these 5. Same thing, the average of these 5 is the same as this one. I just made this up, right? And in fact, when you have a situation like this, you can't really see the difference between the 3 groups. Okay, they all kind of mix together, right? So when you try to draw a conclusion just by looking at a picture, I think you would say that for case 1, the difference between groups is significant difference, right? But case 2, the difference between these 3 groups, difference is not significant, just by looking at graph, right? And the one-way ANOVA F test is based on the same idea, okay? The one-way ANOVA F test actually study the variability between group and also variability within group to see which one is larger. If you have larger variability between group, then more likely you're going to conclude that there's a difference between the three groups. Okay, so that's a term I mentioned here. I have variability between group and variability within group. In my note, I use SB squared, stand for the estimate of variability between group. This is almost like a sample variance, right, for variability between group. And SW squared stand for variability within group, right? Okay, so each of these actually measures some variability pattern, right? This is this is estimating variability between group. This is estimating variability within group. If the variability between group is large, like this one, right, in compared with variability within group, then more likely you're going to conclude that there's a significant difference between these groups, right? So one way ANOVA F-test is actually based on these. I'm going to just jump through this, right? These are the formula for estimating variability between and within group, okay? I guess when you do this, I would like you just run the software, right? You don't have to worry about calculating these, using these formula to calculate these things, right? But actually, this note actually give you these notation, just helping you to understand what's in the formula. So if you really like to try to do this by hand, all right, you can achieve this by using the formula. This is N1, N2, NK. These are the sample size for each sample. X1 bar is the mean for the first group. X bar is the overall mean, right? So this helps you to actually accumulate the variability between group. This is pulling the sample variance information together to help you to get the variability within group. This formula is very similar to the sample variance, pool estimate of sample variance from the two independent sample tests, if you notice, all right? If I make this just two of them, right, and n minus 2, that's really just the same as the variance estimate for two independent sample tests, okay? But anyway, when we do the one-way ANOVA F-test, the null hypothesis will be there's no significant difference between means of those population. Alternative is at least a pair mean difference is significant. Okay, so if you state this, you finish your first step. Now, a lot of times, students will say the alternative hypothesis is mu1 not equal to mu2, not equal to mu3. That means all the mean are different from each other. That's not the case. All right. The hypothesis one-way ANOVA is just at least one pair of mean difference is significant. That's it. That's the complement of the null hypothesis. Okay. Then the test statistic is a so-called F statistic. It's based on the ratio of these two estimates for variability, the variability between over variability within. Remember I say if the variability between is large, more likely you're going to have a significant difference between groups, right? So the larger this number is, the more likely you're going to conclude that there's a significant difference between means. Okay, so this ratio of these two sources of variability are actually the variability measured, right, has a so-called F distribution with 2 degrees of freedom. Okay, 2 parameters. Degrees of freedom 1 and degrees of freedom 2. Degrees of freedom 1 actually associated with the numerator. Degrees of freedom 2 associated with the denominator in this formula, right? Degrees of freedom 1 is number of groups minus 1. Degrees of freedom 2 is total sample size minus number of groups. Okay, so that's the degrees of freedom parameters for this F distribution. Okay, and so as I said, the larger this number is, the more likely you reject the null hypothesis. So when we do this kind of problem, the area to the right of your test statistic will be the p-value. It's the right-sided test. The larger the value, the more likely to reject the null hypothesis, right? So it's a right-sided test. So if you have a table, you will look for the area to the right. The table actually gives you the tail area. So if you have F score, you go to the table, look for the correct degrees of freedom, and try to find out what right tail area associated with it. Right? That would be the p-value. Of course, different sample size, you require different F distribution. So it's very hard to produce this F table. Right? So most of the textbook give you a few pages of information about F distribution, but still not good enough. Right? So it'd be good if you use a software, right? It'll simplify the problem, right? But anyway, we'll look at that in a little bit, okay? So we look at that F distribution in the table. So what are the assumptions behind this one-way ANOVA F test? For you, I think you would just run this software, right, for WebAssign too. But our assumption behind this one-way ANOVA F test, first is you have independent random samples. This is the same as two independent sample tests. You got to have two independent random sample. Okay. And then you need to have a normality assumption, just like two independent sample tests. Remember, this is like an extension of two independent sample tests. So if I have three samples, then you have to check normality of all these three samples. Okay. And then when we know F tests have another assumption that is equal variance. Okay. We assume that all variants are the same. So in order to use F tests, for one-way ANOVA F tests, you got to check equal variance assumption, definitely. Right. If variants are the same, then you can use this F test. If variants are not the same, then you have problems. Right. But there are other methods to do this. There are non-parametric methods that you review this week. Right. If normality assumptions are not good, homogeneity of variance is not good, you can use non-parametric tests for it. And independence, a lot of times students ask me, how do I check for independent? Actually, there are tests for checking independent. However, while you're collecting data, in that sampling process, you should already try to take the independent sample that will satisfy the independent sample assumption. Right? So it's not something that you can check. It's something in your design. Right? When you design the data collection, right? I want sample from independent population, and you'd have independent sample. And randomness, again, it's from your design. Right? Did you randomly pick the subject? Right? Okay. If you deviate too much from it, then the test itself will have less power in telling you the correct information. Okay. So here is an example. We are trying to study whether there's a significant difference in average weight, birth weight, for infant from different types of mother. There are 4 types of mother. Okay. So this is the data. We have infant birth weight for 6 infants from mother type 1, group 1, all right, mother not a smoker. And group 2, ex-smoker, we have 5 observations, 5 infants birth weight. Group 3 is current smoker, smoker less than 1 pack per day. And these are the birth weight. And then group 4 is current smoker, smoke more than 1 pack, or less than 1 pack and more than 1 pack. So you have these birth weight data. You want to see whether there's anything different in average birth weight from different types of mother. Right? So what you can do, you can calculate the sum of square, actually the variability between group and variability within group using the formula that I mentioned. Okay. Hypothesis, of course, mean are all the same. Alternative is at least a pair of mean difference is significant. So if you like to, you can write this a sentence, all right? Or you can write an expression like this, right? Since I have 4 groups, right? So you have mean is different. Mean of the J's group and I's group is different, right? Or at least for mu I is not equal to mu J for at least 1 pair of IJs, right? For IJ 1 through 4. Some of you, I think you don't like that, right? But this is one way mathematically you can describe that. Or you can just write a sentence saying that there's at least, the difference is significant for at least 1 pair of means. That's good enough. Right? So the test statistics ratio of these 2 quantities, we have mean and standard deviation and sample size. For all these samples, I can use these information into the formula for calculating SB squared and SW squared. All right, so that's the formula. From SB squared, you get 5.537. SW squared, right, is 0.609, and ratio of these 2 give you the F test statistic, okay? And then you can use this F test statistic to figure out the p-value for this F statistic. It will be area to the right of this F distribution. And the F distribution will have degrees of freedom, 4 minus 1 and 24 minus 1, okay? Happen to be just these denominator, right? Number of group minus 1, that's the first degrees of freedom. Total sample size minus number of group, that's the second degrees of freedom. Right? That's the 2 degrees of freedom parameter values that you need to use for this F distribution. Right? So I actually use the software. I find out that p-value is 0.00534. If you use a table, you got to use that pair of degrees of freedom. Look up the table. If you want to do the critical value approach at 5%, then you've got to find it. Use the information 5% in the F table to figure out what's actually cut off. In fact, that cutoff is 3.1, right? I think I have an F distribution table, yeah. So this is a typical F distribution table look like. They will give you the degrees of freedom numerator, or degrees of freedom 1, which is the numerator degrees of freedom. And on one side, they give you a degrees of freedom for denominator. So I have this 20, remember 24 minus 4 denominator degrees of freedom. And the degrees of freedom was for numerator is, or degrees of freedom 1 is 3. That is 4 group minus 1, right? Now, if you want to figure out the cutoff at the 0.05 level, that's 3.1. Area, this right tail area, or tail area, right? So if you have an F score that's 3.1, its tail area is 0.05. So if I calculate F score, if that F score is just 3.1, then p-value is 0.05. But my F score actually, if you go back, is 9.088, right? In this table, degrees of freedom 1 is 3. You have 8.1, and its tail area, for degrees of freedom 20, its tail area is 0.001. So if your score is 8.1, F score is 8.1, your p-value is 0.001. Our F score is 9 point something, so we know that our p-value is definitely less than 0.001. So if you use a table, you can draw a conclusion right there, right? Knowing that p-value is definitely less than 0.05. I hope that makes sense, right? Also, so this is trying to help you to kind of estimate what's a p-value like, okay? And then, yeah, then that's a p-value, okay? For 8.1, the p-value is 0.001, right? Our is 9.088, so you know that p-value for our statistic actually even smaller than 0.01. So you can draw a conclusion based on the information you found on the table. Okay. Now, if you have a test statistic whose score is, for instance, 3.7, just for instance, right? Then 3.7 is in between these two numbers. If that's the case, if I ask you what the p-value is, then you're going to tell me the p-value is in between these two numbers. Okay. If it's from a f of 3 and 20, numerator degrees of freedom is 3 and denominator degrees of freedom is 20. Right? So if I ask you the range of p-value for a statistic value is 3.7 in the same setting, right? You're going to tell me that, well, the p-value is between 0.01 and 0.05 based on information from table, F table. Okay. Now, our situation, we have 9.088, which is below 8.0. So if I ask you to give me a range, you're going to tell me that it is less than 0.01. Okay. Now, if you have a score that is 3, then its p-value will be what? Since 3 is in between these two numbers, 2.38 and 3.1. So if you have a 3, then your p-value is between 0.1 and 0.05. So that's going to be higher than 0.05. If you test this at 5% level, you're not going to reject null hypothesis. Right. Hope this helped you to understand how to use that F table. Okay, and then either Pagano's book or WebAssign book, they both have an F distribution table that you can use. Right. Since you're doing WebAssign on the which uses a WebAssign book, right? So if you try to answer a question for WebAssign, try to use that table from the WebAssign textbook, right? The appendix for WebAssign. And this is our commander output. Our commander output, look at that p-value. It gives you the exact p-value, 0.000534, which means less than 0.05. You can draw your conclusion. Okay. And
Professor, do those stars between those RF codes mean anything?
Yeah, these stars actually just giving you a hint, right? When you have here, like when you have one star, let me see. When you have 2 stars, that means that the p-value is less than 0.001. If you have 1 star, it means the p-value, right, is less than 0.01. So it's significant at 0.01 level. If you see a period, that means significant at 0.05 level. If there's, I think that's what? It's blank, whatever, right? That's above. That's another category. Actually, you want to see whether there's star or not, or period or not, right? 0. Oh, okay. I rated it the wrong side, right? When you have 3 star is level at 0.001, 2 star at 0.01, and 1 star at 0.05. Okay, that should be how you read it. Right? I wonder why there's 0 over here. Okay, just giving you, that's typical. And a lot of time when people reporting significance with a table, especially in the regression situation, oftentimes you see people using these asterisks, right? 1 star, 2 star to indicate how significant the evidence is. Right? Okay, hope that makes sense. Right. And just kind of a quick explanation of things that is in a, this is called analysis of variance table. Okay, in the analysis of variance table, you have this mean square. This F 5.537 is really just the sum of square, actually the estimate of variability between group, and this 0.0609 is estimated variance within group. Right? And the ratio of these two numbers give you this F value. Okay, and here in the ANOVA table, these two are the degrees of the numerator and denominator degrees of freedom. Okay. Okay, then after you're done with ANOVA, if you do find significant difference, right, you don't know where the difference lies, then what people do is then go into each pairs and try to see whether the difference lies. That's called multiple comparison. Okay. Sometimes people call it post hoc analysis. Right? Once you found something, then you want to then analyze the difference, find the difference. So if you write R commander for one-way ANOVA, it automatically give you these multiple comparison, comparing a pair of means pair by pair, right, using so-called the two-keys contrast, two-keys methods, right, for comparing difference between two means. And they give you the confidence interval based on two-keys contrast, right? And so if you look at this, this is the ex-smoker, non-smoker, right? So ex-smoker and non-smoker, the difference, you want to see whether there's a difference. So the average between the two is 0, okay? And so you try to find the estimate between the two. The estimate is negative 0.61667, and the confidence interval estimate for estimating a difference between these two groups of mother, average birth rate from these two types of mother, is from negative 1.9 to positive 0.7. You have an interval that actually covers 0. That usually also implies the difference between these two groups is not significant. Okay. Also, the moderate versus not, right? Testing whether the confidence interval estimate for the difference between the two. You get a negative 3.0 to negative 0.5. So it covers a range of negative number. Generally, it also implies that the difference between these two is significant. And the moderate smoker is actually, this is negative, so actually has lower on average birth weight than non-smoker. So these are all confidence, lower bound and upper bound for confidence interval estimate, all right, for the difference between the mean for the different pairs of average birth weight. Okay, I might actually say different pairs of mother groups, all right? So if you look at this fifth one, negative 2.6 to negative 0.06, again, this implies that the difference is significant in the range. That's comparing heavy smoker versus ex-smoker, so difference is significant. And this, the fourth one, actually from negative to positive, that means what? The difference is not significant. So from moderate smoker to ex-smoker, the difference is not significant. Anytime you see a confidence interval cross 0, that means difference is not significant. Okay, this is based on interval estimation. And they use so-called 95% family-wise confidence interval. That means they try to use 6 confidence interval, and the overall confidence level is still at 95%. Right? So when they do this, they actually adjust the confidence level so the overall all 6 confidence level, the overall confidence level is not at 95%. And this is the output from our commander too. They help you to visualize the difference. They just draw those confidence interval, right, for difference between two mean on the chart, and its dashed line is 0. So you have this interval covered 0. That means these two difference is not significant. This interval covers 0. The difference between these two statistics is not difference is not significant. And likewise, this group too. Okay. They also give you the t-test. Right, paired t-test, right? But this is based on the two-keys contrast too. So that t-test is slightly different from the t-test that we just learned. This is based on the analysis variance set up, right? So they give you a t-test, t-value here, and the p-value for the t-test is For this first one, it's 0.57. That means the difference between these two is not significant. And this one, 0.003, 2 star, means what the difference is significant. And this is significant at 2 star at 0.01 level, okay? And again, 2 star at 0.01 level. And then the difference between mid and X, the above 0.05, all right? So this is not significant different than 0.05. This one is significant different than 0.05, heavy and X smoker, because you have a p-value less than 0.05. Okay. So you have two. This is actually for using the t-test, right? Pairwise t-test, and you have this is using confidence interval. But either way, or will give you some idea where the difference lies. Okay. And Archimedes also give you a chart like this. You see there's a not smoker, X smoker, medium smoker, and heavy smoker. And you see these symbols. You have C and C in these two categories. That means what? These two different is not significant. You have a B and B in these two categories. That's what? Different between these two are not significant. And you have A and A for mid and heavy. That means what? Mid smoker and heavy smoker difference in birth weight are not significant. So with chart like this, what they're trying to do is identify homogeneous subset. Right? They try to do some grouping, help you to identify some groups so that difference within group is not significant. So they actually identify 3 groups here. Right? There is a possibility that maybe you see A that is in X and mid smoker and heavy smoker. If that's the case, that means there's not significant difference among these 3. Okay? Hope that makes sense to you? Okay? Homogeneous subset. It's important to do that because, for instance, if you are developing maybe a drug, right? You're developing a drug and you use a different dosage. You try to experiment, try to understand the effect from different dosage. So you have like maybe 4 treatment groups, and the first group is like a control group, right? Nothing applied to them. Then you have first treatment group using 1 dose, and then second treatment group maybe using 2 doses, right? And then third one using 3. Now, if you do this average outcome, right, comparing average outcome from these 4 groups, you find out that the first, second, and the second group, third group, and fourth group all have an A there. That means the outcome from these 3 statistically different is not significant, right? In that case, it'll help you to make decision probably, right? Usually, if you use drug, there are side effects, so probably use less. If you still get similar results, why not just use that since they're all within 1 group, okay, the different amount of those 3 are not significant. So identify subgroup has an important application there. Okay. I hope this makes sense, right? So and sometimes people also draw these so-called error bar chart. Pretty much these are like confidence interval estimate for the different means. Right? I have 4 means, so you have confidence interval there. So you see this interval doesn't overlap with this interval. That means these 2 different is quite significant, right? Same thing, this one and this one don't overlap. That means difference also significant. Sometimes people can look at that to do some visual comparison. Okay. And earlier I mentioned family-wise confidence interval. That is, we try to actually adjust these confidence level so that overall confidence interval is 95%. Or when we try to do hypothesis testing, remember I said that when we do test hypothesis, if we do too many tests, we're accumulating type 1 error, right? Can we control the type 1 error so that overall type 1 error is maintained at a certain rate, right? Here it's called Bonferroni adjustment method. That is, try to control so-called experiment-wise type 1 error, right? So have a family-wise type 1 error, right? While your experiment-wise type 1 error. So overall type 1 error control at a certain level. What you can do is, this is just an estimate. Right? So if comparing 3 groups, I need to do 3 comparisons. So what will be the alpha level I should use? Right? If I want to do t-test and do it 3 times, right, comparing these 3 groups, I want the overall alpha maintained at 5% level. What can I do to control the overall type 1 rate to maintain at 5%? This suggests that once you have an overall type 1 error rate there, you just divide by number of comparisons you need to make. So I have 5% overall type 1 error. If I have to do 3 comparisons, I divide 5% by 3, so I get 1 point something, right? 1.2 1.8 or something, right? So each test I use 1.8% as an alpha to make decision. Right? So overall, I will have 5% in total type 1 error rate. So I would not have inflated type 1 error. Okay. And to do confidence interval, we do the same thing. So originally overall we want to have a 95% confidence level. I can adjust this alpha. So make each of these alpha smaller, so overall confidence for each of those is higher. So the cumulative type and the confidence stay at 95%. Okay. So that's what this means actually when you say the family-wise confidence level. We actually control the confidence level. So overall confidence, I should say adjust the confidence levels, right? So overall confidence level will still be able to maintain the 95%. That's what it means, right? So I hope that makes sense to you. Okay, and a lot of times people like that, right? Instead of having the really presenting a set of confidence interval, but overall confidence level is lower. We don't want that, right? So that's the case, right? I think that's probably all.
Hi, Professor Chang.
Yes.
Quick question. In terms of that, the third to last slide that you had in the slideshow, the argument or output for the error bar on the line graph, yeah, that one right there.
Okay.
For generating one of those in R Commander, we go to graphs. Is it the line graph, and is there an option to draw the error bars?
I think so. Tell you the truth, I can't remember when I draw this, how I draw this, right? I can look for it. I wonder if actually it automatically draws this. When we do the one-way ANOVA, does it draw that? I think that it has graph function that can draw this. I don't know whether they give you those lines connected to that. But you can draw that with R, though, okay? There are options to draw those, okay? Okay. Let's look at that. You know, later on, let's look at that to see whether we have option for that, right? But there are a lot of great graphing capability or package in R that can do a lot of nice graphing. Okay. So let's see that, right? We're going to play with R Commander right away, right? And when we reach this point, see if it has that. I think this is probably given automatically. Okay. Let's look at that. Have you tried it? I wonder. I couldn't really see who asked the question, right? But
we did, but it comes out the first graph, not this one.
Somebody said the first graph comes out sideways. I don't know. I didn't even get a graph after I ran it.
okay. Let's see what happened. All right. And if I can do it, I will explore, right, to see how I did this. So I shouldn't do that. Okay, good. So actually, the next one is just an example how to use a Bonferroni approach to do the family-wise or experimental-wise confidence interval, right? So let's not worry about it. We have the software to take care of that for you, right? So let's take a maybe 5 minutes break, right? So let me sort these things out, and we're going to go over some examples and see how we use the R Commander to do this. So what time is it? Oh, wow, time goes fast. Okay, so we still need 10 minutes break, right? Take a 10 minutes break and come back at my clock here is 10:46. So come back 10:56, and we'll go over R Commander, right? Okay, I hope you're all back. Is everybody back? Let me see. Cleveland, let me test the audio. Cleveland, can you hear me? Cleveland?
Yes,
Okay.
we can hear you.
Okay, great, thank you. Akron, you?
Yes, we can hear you.
Okay. Ohio, you?
We can hear you.
Okay, good, good. Okay, so let's start. What I'm going to do is actually, there's a set of notes for multiple sample things. I just show it over here. Actually, let me show it here, Elmo. Okay. In week 8 week, week 8, right? Same thing, right? So I'm going to go over these example and show you how to use argument to do it. And for those that are in a lecture note, right, you can actually go home and try yourself and see if that works, because you also have output in the lecture notes, right? So you can try to enter the data there at home and try to practice the argument, or you just go directly to the assignment or the web assignment to practice those problems, right? So let's look at this first problem, right? This first problem is a pair sample test, okay? How do we, I think we haven't gone through this yet, right? Pair sample test, multiple sample test, right? So here is just comparing BMI. I have 7 subjects, and before and after, we want to see whether there's significant reduction of BMI, right? At 5% level is significant. So reduction means if you use before minus after, right, you expect to see mostly positive numbers. So if you use before minus after, you want to see that on average, that difference before minus after is greater than 0, right? So if that's the case, this is paired data, so we got to do the pair sample t-test, so that's a test you do. And the hypothesis, null hypothesis would be what? The average of the pair differences is equal to 0 versus the alternative is average of pair differences is greater than 0, right? So that's what we want to test. So this is really one sample t-test, right? You have to prepare for the data, so you use the before minus after to get the difference. So you get 1 for the first pair, 0 for the second pair, 28 minus 24 fourth, third pair, and so forth. You find all the pair differences, and then find the average, right? So get the average is actually 1.714, and you calculate the standard deviation for these data, you get 1.704. And degrees of freedom for the t-test, since you have 7 pieces of data, so it's 6, okay? Then you can compute the t-test statistic, subsample mean minus the mean under null hypothesis divided by standard deviation over square root n, you get 2.66. So use a 2.66, look up a t-table, you'll find out the range for p-value is between 0.01 to 0.025, right? Depends on what kind of t-table you use. Pagano's book, you will get that. Using the web assigned book, you probably get a more closer p-value estimate, right? But you can use the argumenter to do it, you get a p-value of 0.0188, okay? This is the right side of the test, so you're looking for error to the right of the test statistic, 2.66 from a t-distribution. So then the p-value is less than 0.05, so you can say you reject a null hypothesis since the p-value is less than 0.05. Then, again, you want to comment on alternative hypothesis, right? You have sufficient evidence to support the alternative that the average reduction is greater than 0, okay? So that's how you do this by hand, right? If you do this with SPSS, SPS, what I'm saying, Argumenter, right? I think I didn't have enough sleep again, right? So we still have 1 hour, okay? So I should be okay. So let's see how we do this problem. What we need to do is actually, since this one actually, this is not testing whether the difference is greater than a certain number or not. We can use a pair sample t-test to do this, but my preferred way is still calculating the pair differences, right? So let's try this. We're on PC. Okay, so let's try to create this data. New data. I'm going to call this data set 1. Click OK. And I have 7 pairs, so I have to have 7 rows, right? And then I have to add 2 more columns. Oh, actually, don't need 2 more columns. But anyway, start entering data, 30, 27, 28, 26, 29, 27, 29. Okay, so that's first column. 29, 27, 24, 26, 25, 26, 27. So that's how you set up your data. The first subject, you observe two pieces of information, right? The first one was actually before. The second one was after. Okay, so you got these observation entry. That's how you do it. Okay, so you got the data there. Then you need to process this data a little bit. You want to compute new variable. The new variable, I'm going to call it the DIF, the difference. And that difference is, I say before minus after. Right? So before, click before, type a minus, and click after. Okay, maybe leave a space there. I guess it's okay. So before minus after will give me the difference. So that's how you actually create another variable called difference. So let's go to the data. I have that different. V3, that's extra, right? So let's not worry about V3. Difference is that actual difference, okay? So we can do one sample t-test on these paired differences to test whether the average of these paired differences is, in this case, is greater than 0 or not, okay? The good thing of doing these differences is that I can check for normality. But you know the sample size is small. Usually you're going to pass a normality test. But anyway, we can do that. Click Statistics, Summary, Shapiro-Wilk test for normality, difference, click OK. 0.11, pass the normality, right? Pass the 0.05. So normality is okay. Right? Then you can do the t-test. Click Statistic, Mean, Single Sample t-test on that difference. And you want to test whether it's greater than 0 now to check on population means greater than mu 0. And then click OK. You get a test. That's what I have there, right? 0.018, I'd say 0.0188, but here is I round up to 0.0188, right? This is 0.01873. So that's testing for mean greater than 0 or not, okay? You can do statistic mean pair t-test and choose before and after and click OK. I'm sorry, option. Test for difference greater than 0 or not. I click OK. I want to do one-sided test. Right? And click OK. And you get exactly the same outcome. Okay? But doing the way I did, you are able to check for normality. Right? So I actually prefer the way I did it. Okay? But if you want to quickly get a result, right, without going through this computing variable, getting that pair differences, then you have an option to do that. So that's how you do this first question. Right? Any question? Do you have any question? To use the R commander, right, and also just do hand calculation, right, for doing this pair sample test. Right? So you see, this is really just one sample test. Although it says pair sample t-test, it's really one sample test on the pair differences. Okay. Now this one, second question, we actually have two samples from two different populations, right? You see, although the data are the same, I've just made up these data. They have the same value, okay? However, this one is treated as a pair sample. We actually have 7 subjects, and each one observed twice. This one actually is from 2 independent populations. So we have 2 independent sample t-tests. This is a situation you need a 2 independent sample t-tests, right? Goal is still to see whether there's a significant difference or not. So the null hypothesis will be what? Difference of the mean is 0. Alternative is, heck, actually here we want to see whether there's significant difference or not. So it's a 2-sided test, right? By just this information given in the problem, right? So we want to do 2-sided tests. So what I do is I'll calculate the mean and standard deviation from each sample, right? Mean for this, standard deviation for this, mean and standard deviation for this. And I plug into the t-test statistic. And I'm assuming equal variance. Okay, if I'm assuming equal variance, actually this is, I take the approach for the Web Assigned book, assuming not equal variance, right? So each sample variance will estimate it. Each variance will estimate the sample variance, right? Plug them in there. First mean minus second sample mean subtract 0. That's a different we should test is 0. So that's 0, right? So I calculate this. I get a statistic 2.121. Then I use the degrees of freedom formula to calculate degrees of freedom. That's 11.815. So with this degrees of freedom and this t statistic, you can use Excel to help you to find an exact p-value, right? Or you can use a t-table to help you to get a rough estimate. Okay, so I got a p-value of 0.057. And this number just not less than 0.05, right? So we do not reject null hypothesis. So you're going to conclude that the evidence is not sufficient enough to support that there is a significant difference between the average weight for these two populations. Okay? Now, hopefully from this example, you realize the difference between these two tests. We have same data. When we do the pair sample test, the p-value is this small, less than 0.05. But when we do two independent sample tests, the p-value actually above 0.05. This is telling you that two independent sample tests will have a larger standard error, so your t-score will be actually smaller than if you use a pair sample test. Okay, if you calculate this part especially, this part from t-score, from pair sample test, this is standard error, is smaller than this number in the denominator when you standardize the test statistic. Right, so pair sample test actually is more powerful, right, because it has smallest standard error, right? But it's for different design, okay? This one is for independent sample. That one is for pair sample. So you have to use the right one. If you use the wrong one, you have you're actually giving people the wrong information. Okay, so you have to be careful. Now, how do we run this with SPS? Yes, R commander, right? I'm teaching another class actually using SPSS, so I keep using that term. So R commander, let's create a data. R commander, let's call this data set 2, okay? Then at row, I have 7. I'm going to continue adding, right? Because this is a two independent sample test, so we actually have 14 subjects, right? So the first subject, let me get this here. First subject is 30. Second is 27, then 28, 26, 29, 27, 29. So that's first sample. Then 29, 27, 24, 26, 25, 26, 27. So I got the data there. Now I have to create another column. This column is for identify which sample it is, right? So I can 1 to the first sample, and 2 the second sample. Right, so I'm going to call this first one BMI. Second one I'm going to call it maybe group or population. Okay, and click OK. So I got my data ready. Right. Now to do this test, it's not hard. Right? You have statistic, means. Oh, two independent sample tests is not available. Why? Because the group variable is not categorical, right? So what you need to do is click Data, Manage Variable, Convert Numeric Variable to Factor. Right? That will help you to actually define the group variable, make that factor. So I'm going to make it easy. I just use number and click OK and override that. Right? If I do that, now this time, although it's still 1, 2, but they are categorical, they are factor. Then if I click Statistic, Mean, it'll be activated. Right? Independent sample t-test. So it's all set up, right? An option is do two-sided test. And is assume equal variance? Well, we say no. And that's the approach I took too. And by default, our commander also use not, right? Use no. So I click OK. I got my p-value, 0.05575. Right, that's, well, actually, don't know why. Oh, okay. I was doing the hand calculation, all right? So my answer was a little bit off from what they have there. Mine is at 0.057, right? With the software, you give a more accurate number. So this is how you do a two independent sample t-test, okay? And if you want to run normality, unfortunately, at this point, I don't think it has an option for normality for subgroup, yeah. So if you want normality for subgroup, what you can do is actually, if you remember, some of you probably have done this already, check my actually website. There's a by function that actually allow you to do normality tests for subgroups, right? So the syntax is this. You use by and parentheses, the variable name for that quantitative variable, and then the variable name for that qualitative variable. And when you specify the variable name, you have to have a data set name first, and a $ and variable name. Because while you're running that R command, you may have so many data set in there. Okay, so your data set name, $, variable name, and first one is that quantitative, second one is that group variable, right? Now, if you cannot remember, I want to see if I can copy and paste that in the R commander. Let me see. So we can do that in the R script section. I copy and paste. Oh, it's good. All right, so I copy it in there. But the data set should be data set 2, right? We call data 2. How do you know that? That's over here. The one that is activated is data set 2, right? That's what you're running. So these should be data set 2. And the variable name, the first one was for BMI, right? BMI. I hope I named that. Second one, I think I named it as group. Okay. Then I just highlight this line and click submit. I got both normality tests. For the first group, p-value is 0.75. Second group, p-value is 0.87. So normality tests are good, right, for this. So I can use that conclusion, right, for this test. So that's 2 independent sample t-tests. That's pretty easy with the R commander, right?
Quicker check.
Yes?
Where was that on your website, please?
Where is what? Oh, website. Okay. It's from my R instruction page. Go to my page, R instruction page. You can go directly to R instruction page from one of the course material link URL page section in the content section of the Springboard, right? But anyway, that's my R instruction page. If you go down to
It's actually in the instructions for the ANOVA.
it's also, yeah, okay, that's good, yeah. So I try to have that maybe sometime, right, in many places, but this is the one, right, that I have, that I just showed you from our instruction page. I think I have it in many places. Also, I had it here in the video too. Subgroup, okay. So you click on that, you get that command line, right? Okay, good. So that's actually for 2 independent sample tests. For what if I want to do ANOVA? This is an example for ANOVA. I have 3 populations now, right? So 1 extra, right, than what we have earlier. So over here, we want to test whether there's a difference between the 3 population means, right? So this would be, if normality assumption is okay, equivalence assumption is okay, we can do one-way analysis variance F-test for it. So the null hypothesis will be all means are the same. Alternatively, see, that I wrote that as phrase here, at least a pair of mean are significantly different. I mean, or there's significant difference between at least one pair of means. Okay, so the test statistic is the ratio of these 2, right? If you do it by hand, you can get the result. And actually, I cheated. I just use a software result. Right, I get the 18.035, and also the p-value report from the software. It's so small, so I reject null hypothesis. Okay, and to do this with the R commander, right? Let's go to R commander. Actually, I can just extend this one, right? So let me view add a data set. Actually, it's the same data, I think. Yes. All right. Just add extra rows. So I'm going to start adding 3 more rows. 7 more rows, I should say. Right? So this would be 33, 32, 29, 37, 30, 38, 35. Okay. Then the group should be 3. Okay. So I got them all. I'm going to click. Oops. Okay. Right. Now there's maybe a problem if you click statistic and mean. The one-way ANOVA may not show. That is because you enter some numeric variable. So you can go back to the data and then do the convert numerical variable again. I click group and make that factor, and I just use a number, okay? So I don't create a new variable. Click OK. Now it should be ready. Means and one-way ANOVA should be ready, okay? Hope that makes sense, right? If I move too fast, let me know, right? So I click one-way ANOVA, and the group variable, only one group variable, one quantitative variable, so it's all set up. But if you want to do those multiple comparisons, or called pairwise comparison of mean, you're going to check this box here, okay? And you need to do that for assignment. I think I asked you some question, right, for this. And click OK. Then you get this nice chart, right? Family-wise confidence level, confidence interval. So this tells you the group 2 and group 1 difference not significant. 3 and 1 different significant. 3 and 2 different is significant. Okay. Let me close this up and go back to the top. You have this. This is the p-value for the one-way ANOVA f-test, right? This is that f-test statistic. This is the p-value for the f-test. Okay. And this is, remember this notation, scientific notation, this is 5 times 10 to the negative 5 power, right? Negative 5th, okay? Then they report the mean standard deviation for each group. They also give you this Tukey's contrast, right? For t-test for each pairs. So you see 2 and 1 p-value is 0.3 is not significant, but 3 and 1, 3 and 2, different is significant. Both are less than 0.01. Okay. Then you can see the confidence interval. You saw that in my slides. Also, you look at this one. This is identifying subgroups. So this tells you that group 1 and group 2 different is not significant, and group 3 is standalone. Right. So 3 and 1, 2, right? They're different from each other. Right. Group 1 and 2, there's no different amount, but 3 is significantly different from 1 and 2. Right. This gives you 2 subgroups there. 1 and 2 is a group, 3 is a group. So that's one-way ANOVA. Okay. Now, if you wish to do round normality tests, again, you need to do something similar to what we did there. Where was it? You go up. We just did a normality test, that by statement. The same by statement. Remember, we just used the same data, but we just added a third group. So this will still work. If I click on that and submit, I'm going to have 3 normality test results, right? The first one, high. Second one, still higher than 0.05. Third one, also higher than 0.05. So I'm set. Okay. And there are other places you can check for model assumption, right? We run ANOVA model, actually. You see this ANOVA model.1. That means the current analysis ANOVA model, and there will be some data stored somewhere in the workplace, right, in this system. So you can use those data to also check the model. You click on model, there are things you can find. You can do confidence interval. You can do hypothesis testing for ANOVA, linear contrast from Tukey's, but let's look at this graph. You do basic diagnostic graph. You also can do the so-called quantile plot, residual quantile plot. This will be also one thing that you can do to check for normality. If you click on that and click OK automatically, you see these, this is a quantile plot. Quantile data versus quantile residual, right, which is error distribution versus the quantile of a normal distribution or t-distribution, right? It actually, all the dots fall into these 2 red dashed line. That generally means that the normality assumption is okay. Okay, so this is almost like plotting quantile data versus quantile distribution about the normal distribution, right? So also, if you click model graph, let me see, effect plot. This is what you just asked. You have effect plot, and then click OK. You see, this is a line that you just asked. Okay, they do the error bar chart and also draw the line, connect all these together. Right, so it does have that function. Right, if you check the effect plot. Okay. So if you click on model and then, let me see, actually not there. If you do the numerical diagnostic, and there are tests for heteroscedasticity, right? This is for checking equality of variance assumption. So if you click on that, click OK, you get a p-value. Wow, we do have a little problem here, right? There's another place you can check that. You click Statistic, Variance, and Ballot or Levin's test for equality of variance. You click on that, and then it uses a median test, nonparametric test, and you click OK. You also get the p-value from there, right? And the p-value is 0.04958. So I do have a little bit problem with my data, right? My equality of variance assumption are not quite there, right? When I do this nonparametric test, I actually have a p-value is close to 0.1, below 0.5. So kind of you're going to reject the equality of variance assumption. Okay. So you have to do this. This is one assumption behind the analysis of variance test that you have to check. Okay. It seems like I have some data that has probably larger variance than the other or something. Okay. Now, when you do have a situation like this, or you have violation of normality, then there's that Kruskal-Wallis test. You probably have reviewed that nonparametric test, Kruskal-Wallis test, a nonparametric alternative for one-way ANOVA. Okay. And you can do that. Right, if you do have violation of these assumptions when you do a parametric test, a one-way ANOVA F test. Okay. Okay, makes sense? Right. So, since I guess that's okay. You guys have studied the nonparametric test already, right? You have nonparametric test alternative for one-way ANOVA. And I just mentioned this is one-way ANOVA F test. If you want to run that one-way ANOVA nonparametric test, you click Statistic, nonparametric test, Kruskal-Wallis. That's a nonparametric alternative for one-way ANOVA F test. If you click on that, and it's all probably picked, right? Group variable is just group, and response variable is BMI. You click OK. It gives you a nonparametric test result. It's actually an extension of a Wilcoxon range sum test called Kruskal-Wallis test. Right? You have a p-value of 0.001. That's very small, so that means there's significant difference among these three populations. Okay, so that's if you have violation of condition in the one-way ANOVA F test, then this is the alternative for it. Okay. And of course, we run the pair sample test. There's a non-parametric alternative for that too. Okay. For let's go back to that one. If you want to flip between data set, you click on that. Click on this button. You can go to data set 1. Remember, data set 1 was pair sample situation, right? There is non-parametric test for pair data, right? That's click Statistic, non-parametric. Pair sample Wilcoxon test. You click on that, choose before and after. There's an option whether you want to do two-sided, one-sided. I think we do one-sided. We want to see whether the difference is greater than 0 or before is greater than after or not, so to see whether there is a reduction. Right? Look at the option here. They're exact and they're normal approximation. Non-parametric tests, it's actually when you have sample that is very small and data not follow normal distribution, that's the situation you want to do non-parametric test. Right? Normal assumption is not true. And the normal approximation is actually large sample approximation. When you do want to use non-parametric test and the sample size is large, usually the non-parametric test, its sampling distribution it varies, depends on sample size. And usually require a lot of computing time to get the sampling distribution. So oftentimes people do normal approximation. So you don't have to get the exact distribution, which you need a lot of time to get the sampling distribution. Right? But I'll recommend your author use a default one, so whichever is convenient and faster. Right? So let's just use a default one. If I click OK, it gives you a Wilcoxon sign rank test. Right? Wilcoxon sign rank test is non-parametric alternative for one sample t-test or pair sample test. Remember, one sample t-test and pair sample t-test, exactly the same test. It's just one sample test, right? So it will give you and the statistic is based on sum of positive rank. Okay, but anyway, if you don't even know your statistic, if you chose the right option, you get the p-value. You just interpret the p-value, right? And you get your results, right? If you choose the right alternative hypothesis, you see the p-value 0.028, that tells you you reject null hypothesis, support the alternative. That actually before is higher than after, that means there is a significant reduction in weight. Okay? I hope that makes sense. Right? I didn't do the lecture or review on unparametric tests. Let me quickly go